Right, very short piece here on orthogonal matrices. We have been talking about them in the context of the Gram-Schmidt process, which gave us this second factorization for us. So, all right, we're going to call these orthogonal matrices. They're really kind of orthonormal matrices. So this is a little bit of an odd thing, perhaps. I mean, if we stick with the orthogonal basis, orthonormal basis story. Okay. All right, so Gram-Schmidt process. Let's look at this. It gave us this A equals QR. This is an upper triangular combining matrix. Q and R have the same shape. It's here and here. And this is this observation, right? So Q's columns form an orthonormal basis for A's columns. For the orthonormal basis for the column space of A. That's what I'm trying to say. So A is a base. Let's presume that the rank is equal to n. So the basis A's columns form a basis. Q's columns do too. Q's are orthogonal, right? And that's encoded here in this piece. In fact, that they're orthonormal, right? So the inner product of Qi and Qj is 0 if I is not equal to j, and 1 if it's equal to j. Which is very nice, right? It's the definition of the identity. Another good thing there is the Kronecker delta. Very good, but we're okay. So this is just a few more things on what Q can do for you, right? We've seen this business, right? We've had to use it a couple of times, so let's just say it again. So Q transpose Q. So it's a left inverse is this word. Left inverse for Q. Right? We just take the transpose. It's great. Boom. That inner product is 1. The inner product with Q2 is going to be a 0, etc., 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 right? So the only things that we get that are non-zero are along the diagonal. We start with an m by m and an m by n, so we end up with an m by n. So it's not quite a complete inverse. It's not obvious how it's going to work if we take the reorder them. But in fact, if Q is square, there's a couple of things we can do, right? So if Q is square and m equals n equals r, the inverse exists, which means the null space of Q is equal to 0, right? Full rank. Then we have this Q transpose. Q is equal to the identity, which is QQ transpose, and of course we know that that's the way the inverse works. And so we say, big deal, the Q inverse is just the transpose, which seems remarkable. I hope you think that's kind of remarkable, because it's a crazy thing. All right, let's see if I can draw a box. Yeah, it's not a bad box. Let's color it in because we're very excited. So the inverse, just the inverse. So inverses are hard to find. If you remember, we had to do Gauss-Jordan elimination. Otherwise do it, I suppose. But that's what we talked about. Lots of row operations. Just take the transpose. Right. So if you know that your columns are linearly independent and they're orthogonal to each other and they're orthonormal, right? So various steps. So the most excellent version here is that they're orthonormal. Then we're going to say that Q is an orthogonal matrix, even though it has an orthonormal basis in there. So it's orthogonal, it's square. There are lots of other properties that follow, and these are things that we get asked in an assignment. Oh, I see what's going on. Q is an orthogonal matrix. Good, 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 good. So there are many other properties, including this. If you so this is transforming x, Q times x, right? The length. So again, this is length. So what does that sort of thing? Something that rotates a vector, maybe flips it, other sorts of things. So length is preserved. Length is preserved under transformation. So that's one thing. The inner products, so if you transform x and then transform y and then find what their inner product is, it's the same as what you had before, right? So that's another, so this is about preserving angles. All right, dot products are about the angles between things. Right, so Q preserves angles. So yeah, rotation is good, right? So rotation, the length doesn't change if we've just got one vector. If we've got two vectors, the angle between them doesn't change as we rotate around. So a couple of examples. So this is a permutation. This is rotation by theta in a positive direction. This is a permutation. So there are a number of great things. We'll come back to some of them. This is an interesting one down here. So these are just examples. So we could use Q to do this. So mostly it gives you back the vector you had. Identity times a vector is the same vector, but it's going to have this piece as well. So U transpose is an outer product, right? That's a projection matrix. So you must always see these kinds of things as projection matrices. Projection onto U hat. So we project a vector onto the U hat direction, and then we subtract 2 times that, right? So the idea is, here's x. X is here. We find the component of x in the U direction. We subtract that off, and then we subtract off another equal amount. So this is 2. Right, so this is, let's see if I can do it. Right, this is minus, this vector here is minus 2u, the projection of x onto the u direction. So we're subtracting it, gets it back to 0, and then we flip it out there. So it's a mirror image with respect to that direction. Right, that has the same kind of property. So, right, these are called orthogonal matrices, square matrices, very natural objects. We are going into looking at square matrices in much more depth right now. There's going to be a number of episodes on this, and it's eigenvalues and eigenvectors and eigenspaces. Determinants become a big piece in there. We'll explore some other funniness in all of that, and then we get into some of the most beautiful factorizations in matrixology, and therefore the universe. Is that okay with you guys? All right.